Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on August 25, 2025, which was about 4 days ago. The standout result is that localized maximum perplexity from an LLM aligns with human brain signals of confusion, showing a moderate and significant Spearman correlation of 0.47 for confusing code. The paper is titled, How Do Humans and LLMs Process Confusing Code? And the implications for developer tooling are quite significant. In short, the study shows that token-level perplexity spikes map to human confusion over atoms of confusion, and a detection pipeline can flag confusing regions at scale. On X, a Japanese post highlights that brain responses indicating human confusion align with model perplexity spikes at difficult code tokens, emphasizing the shared confusion signal and practical uses for flagging confusing regions. Engagement looks solid with about 232 likes. The previous figure summarized the headline correlation, and Figure 1 now illustrates a concrete example. Figure 1 contrasts a confusing Java snippet with a cleaned version, which isolates the post decrement into a separate statement. The middle row shows token-level perplexity bars that spike at the decrement location, signaling model uncertainty. The bottom row presents mean fixation-related potentials over time, and the confusing snippet yields a larger positive amplitude. Together, these panels link localized perplexity peaks to stronger neurophysiological signs of confusion. So the previous figure connected spikes and brain signals, and Table 1 now grounds that link with concrete code patterns. Table 1 lists atoms of confusion alongside a confusing variant and a clean counterpart, which clarifies exactly what code idioms drive uncertainty. Examples include arithmetic as logic, implicit predicates, removed indentation and missing curly braces, plus increment and decrement forms and type conversion. The side-by-side layout highlights that small syntactic tweaks, like isolating increments or adding braces, convert confusing code into clearer intent. Okay, the previous table cataloged the code idioms, and Figure 2 quantifies how strongly uncertainty rises. Figure 2 shows box plots for average and maximum perplexity at snippet level and area of interest level, contrasting confusing in red and clean in blue. The area of interest maximum stands out because it yields the largest separation and effect size, with P below 0.001 and R around 0.45. The snippet metrics also differ significantly, yet the peaks at focused regions drive the clearest signal. Alright. The previous figure emphasized stronger effects at focused regions, and Figure 3 directly links those peaks to brain signals. Figure 3 shows two scatter plots, comparing maximum area of interest perplexity to mean fixation-related potential amplitude. The left panel for confusing code rises with a moderate Spearman correlation of 0.47, so higher perplexity aligns with larger positive brain responses. The right panel for clean code stays flat, with Spearman around 0.05 and a non-significant p-value. Alright, the previous figure contrasted correlation patterns, and Figure 4 visualizes overlap between manual labels and automatically detected regions. Figure 4 shows an upset plot in which horizontal bars give totals per category, and vertical bar stacks show intersections across categories. The tall gray bars indicate many automatically detected regions in both clean and confusing snippets, which supports broad coverage. The purple bars mark overlaps, so detected regions frequently coincide with manually labeled atoms of confusion, though not perfectly. Alright, the previous figure showed overlap patterns, and Figure 5 turns to correlation within automatically detected regions. Figure 5 presents two scatter plots that relate maximum area of interest perplexity to normalized mean fixation-related potential amplitude, separating confusing code on the left and clean code on the right. The left panel shows a moderate positive trend with Spearman around 0.37, which indicates that stronger perplexity aligns with larger positive brain responses. The right panel shows a weaker but still positive association near 0.31. Markers distinguish regions that overlap known atoms versus those that do not. So the previous figure broke down scatter trends, and Table 2 now quantifies them across subgroups. Table 2 reports Spearman correlations between maximum area of interest perplexity and mean fixation-related potential amplitude, with clustered bootstrap confidence intervals. Overlap with confusing atoms shows a significant correlation around 0.33, and no overlap with confusing atoms is similar at 0.36 but not significant. Overlap with clean atoms also reaches significance at about 0.38, which suggests that perplexity-flagged regions align with brain responses even beyond manually labeled confusion. So, two takeaways stand out. Localized maximum perplexity mirrors human confusion signals, and a simple perplexity peak pipeline reliably flags confusing regions, even beyond manually labeled atoms. The broader implication is practical tooling, where models can triage risky code for review or refactoring at scale. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.